section L03, moment of inertia for of a hoop. The hoop's a very, very popular toy. It came out when I was a boy, the hula hoop. And here all the mass is at a distance from the center that's equal. And in this case, let's imagine like really fine like spokes. If there's a fine spoke here and here, so that you could actually put an axis through there, and that the mass that's significant is along here, then you're everywhere a distance r, capital R say, from the center. That's a kind of cool picture where it looks like it's just floating in there. So these are from Flickr, and credit lines are given with each photograph, and they're Creative Commons. Usually you have permission. The ones I use have permission with giving the credit to the author. Yeah, back when I was a boy many years ago, I think it was 1958. So therefore, the moment of inertia, using the formula MI/RI squared, this is going to be, the MIs are all along the hoop. So if we were to look at the hoop like this, everything is a distance r away from the center. So if you break this up into little, MIs, they're all the same distance away, capital R squared. So this is going to be capital R squared. You're just going to sum up all the masses, and that's going to be capital M, the mass of the hoop. So the moment of inertia for a hoop is capital MR squared. It's the same that we did earlier when we had, say, one mass that's a distance r away. It's the same formula. Now here you might imagine, lots of masses like this, so this is going to be a bigger mass, but the same effect. You just simply add them all up. So let's put down here for what we just did. This was one about center of mass. So we could say that the case that we did here, we could actually add ICM. And then for case 2, what we're going to do is the hoop about an edge. So that would be like having the hoop and you were going to go about the edge. It's going to go like this way, back and forth, just hanging it. Or like in this case, the edge would be here, and then you would have the hoop like this, going around the edge like that. So if we're going to do that, we use parallel axis theorem. The parallel axis theorem says I is equal to I center of mass plus md squared. So we're going to displace it by, the d is going to be equal to r. So the center of mass case is m r squared, we already did that, and then plus m r squared. Look how easy this is. So the moment of inertia about the edge is going to be 2 mr squared. Here's another example, picture from flicker where you're spinning this around about its edge. So the foot's there at the edge, and then, it's going around. Next, we'll do the spinning ring, where we have the hoop, and we're going to spin it in this fashion. So that's the third case, the spinning ring. So that's like taking the hoop like this, like a little ring, and the axis we're coming down like this, and we're going to spin it around this way. Well, here we used a perpendicular axis theorem that if we were to spin it around, like say here, go ahead and see if I can sketch this, where this is Z, and this is X, and this is Y. If you go around the Z axis, that has to be the sum of around the X axis and the Y axis, which should be in this fashion. So therefore, I about Z is I about X and I about Y. This is the perpendicular axis theorem. And here, these two are equal. So this is going to be equal to 2I in this case here. So the IZ, about the center, we already have done that problem. That's this one up here. So we have the situation mr squared is equal to 2I. So that means this case is 1/2 mr squared. Spinning the ring. So with these theorems, you could see how powerful it is to get other results. The parallel axis theorem used in this case, and the perpendicular axis theorem used for that case.